Hey there and welcome. There's something happening inside your computer right now, something that's always running, and honestly, it's kind of beautiful. It's this constant, quiet act of tidying up that makes everything, and I mean everything, you do on your devices possible. So, let's pull back that curtain, shall we? So, have you ever really thought about your phone? Like when you're bouncing between a game, then you quickly check a message, then you hop over to your browser. Your phone doesn't just, forget everything about that game. It can't. It has to put all that game stuff somewhere safe while you're doing something else. So, where does it all go? And how in the world does it keep track of it?
Okay, the best way to wrap your head around this is to think of your computer's memory as just this one giant shared storage closet. Seriously, every single program you're running, your browser, your music app, the OS itself, they all have to shove their stuff into this one closet. And in the tech world, we call this big shared space the heap.
Right. And I think we all know what happens to a shared closet when nobody keeps it tidy, right? It becomes a total mess, a nightmare to find anything. And well, it's pretty much the exact same deal inside your computer.
So when this digital closet, the heap, gets all messy and disorganized, you feel it. We've all been there. Your apps get super slow, they don't respond. They might even just crash for what seems like no reason at all. And this isn't just some small annoyance. It's a really fundamental problem that computer science has to solve. And this brings us to a really, really important point. We always think about how fast our computer's processor is, right? But the thing is, performance isn't just about raw speed. It's often all about how well the memory is managed. It doesn't matter how fast your computer's brain is if it takes forever to find its stuff in that messy closet. A tidy closet is a fast closet. Tidy memory is fast memory.
Okay, so who's the brave soul in charge of keeping this closet organized? Well, that's the job of a very special piece of your system called the memory manager. You can think of it as this unsung hero just constantly working in the background, making sure things don't fall into total chaos.
And the heap, well, it's for the important stuff. It's for the data that needs to stick around for a while. It's not for quick little notes you scribble down and then toss. No. Putting data on the heap is more like placing a book on a shelf. You absolutely expect it to be there when you come back later.
So, the memory manager's job really just boils down to two main things. First, when a program needs to store something, the manager has to find an empty spot for it. We call that allocation. Second, when a program is all done with that thing, the manager takes it out and frees up that space so something else can use it. And that's called deallocation. Sounds simple, right? But this is where a really interesting puzzle starts to pop up.
Yeah, this whole cycle of putting things in and taking things out, it creates this super tricky puzzle that the memory manager has to be incredibly clever to solve. Let's go back to that closet. Imagine you put in a big box, and then right next to it, you put a small one. A little later, you take that first big box out. What are you left with? You've got an empty space, sure, but it might be too small for the next big thing you need to store. So now your free space isn't one big useful chunk anymore. It's scattered all over in these little awkward pockets. It's fragmented. Let me walk you through exactly how this happens. Okay, so we start with a nice, big, empty shelf. An app comes along and puts an item on it. Then it puts another item right next to it. But then it decides it's done with that first item, so that gets removed, and boom, you've got a hole. Now that hole is technically free space, but if the next thing the app needs to store is big, that spot is completely useless. It's empty, but it's not helpful. And that right there brings us to the official definition. Fragmentation is that super frustrating situation where you technically have enough total free space, but it's all broken up into tiny little chunks, so none of them are actually big enough to use. It's like having enough Lego bricks to build a whole castle, but they're all just single little pieces scattered all over the floor. So how on earth do you fight this fragmentation problem? Well, there's a really clever strategy called best fit. The logic is pretty brilliant, actually. When you need to store something, instead of just grabbing the first empty spot you see, you look for the smallest possible hole that your thing can just barely squeeze into. Why? Because this saves those big, roomy, empty spots for the really big items that you know are going to come along later. It's such a simple idea, but wow, it makes a massive difference. But, finding the right spot to put stuff is only half the battle. The other half is cleaning up. How does the system even figure out what's okay to throw away?
Well, there are really two ways this gets handled. In older programming languages, like C++, the programmer themselves is the cleanup crew. They have to write code that specifically tells the system, hey, I'm done with this piece of memory, you can have it back. It's super fast and direct, but it's also really risky. If you forget to clean up, you get what's called a memory leak, where old, useless data just piles up and wastes space. Even worse, if you clean something up too early, you get a dangling pointer, which is a recipe for crazy, unpredictable crashes. That's why most modern languages, like Java, use an automatic cleaner instead. We call it a garbage collector. It's way safer for the programmer, but it does have its own set of trade-offs.
Which, of course, brings up a really fascinating question. I mean, if a program is just running along, doing its thing, how can this automatic garbage collector possibly know which things in the closet are still important and which things are just old junk that can be tossed? The whole secret is this idea called reachability. Think of it like this. The garbage collector basically tries to trace a string from the currently running part of the program to every single object in the heap. If it can find a path, any path at all, that object is reachable, and it's safe. But if it checks an object and there's not a single string leading to it, not one connection, then that object is considered unreachable. It's basically lost treasure, and it can be safely thrown away. And one of the most classic ways to do this is a method called mark and sweep. It's a two-step dance. Step 1, the mark phase. The collector finds all the roots. That's the data the program is actively using right this second. Then it starts from those roots and follows every single connection, kind of like a spider crawling its web, and it marks every single object it can touch as in use. Step 2 is the sweep phase. It goes through the entire heap, from top to bottom, and any object that wasn't marked gets reclaimed. It's that simple. If it's not marked, it's garbage.
So when you start to put all these pieces together, the giant shared closet, the busy memory manager trying to solve the fragmentation puzzle, and this automatic cleanup crew, you really start to get a picture of this incredible, totally invisible dance that's happening inside our devices every single second.
And it really all just boils down to one simple, kind of profound idea. In the digital world, to be forgotten is to be garbage. If there's no path leading back to you, then as far as the program is concerned, you just don't exist anymore. So, the next time your phone or your computer feels just a little bit sluggish, just for a second, pause and think about what might be happening under the hood. There's a good chance that a tiny, super efficient memory manager is right in the middle of a mark and sweep, tidying up that digital closet, figuring out what to keep and what to toss out, all so your app can get the space it needs. And that really is what heap management is all about. It's so much more than just some dry technical process. It's this quiet, invisible system of elegance and order. It's the constant, hidden effort that keeps our incredibly complex digital world from just falling into chaos. Just a little bit of tidiness happening billions of times a second, making everything else possible. Thanks so much for taking this little peek behind the scenes with me.